Hi, welcome you all on Physics Addhyan. And in last lecture, we have studied about the diagonalization of a matrix and we did some problems. And today's lecture, we are going to deal with coordinate transformation, that is via rotation. So let's go to a transform frame. So suppose that is your axis O, origin O, that is your, let's say this is your x-axis and its unit direction is I cap. This is your y-axis, its unit direction is your j cap. So suppose there is a position vector at point R. Its position vector is given by, let's say this is R. Its coordinate is x comma y. Okay, so simply in this O coordinate system, that is x comma y, we can write this r vector as x times I cap plus y times j cap, and you all agree with this. Okay, so let's move further. So suppose I have rotated my transform system such that my new transform coordinate axis is somewhat look like this. Let me draw the similar axis for y. So from y, let's say this transformation happens like this. It means that this axis x is rotated by an angle theta. Similarly, angle y gets also rotated by angle theta. Let's call this new system as x prime and y prime. Let's the direction, these directions will be I prime and this is j prime. Okay, so this same vector r vector in O prime coordinate system, let that position is x prime comma y prime. In this new coordinate system, the position at this particle P will be x prime comma y prime and the vectors remain same. So this r vector will be written as x prime I prime plus y prime j prime. Because the vector is the same for both the transformation, so we can write it as x I cap plus y j cap is equal to x prime I prime plus y prime j prime. Okay, now let's do this thing. Okay, so from 1 we multiply both sides with I cap. That is the, let's do the dot product. Okay, so when you do the dot product, it will become xi dot I plus yj dot I is equal to x prime I prime dot I plus y prime j prime dot I prime. Since the modulus of I is equal to modulus of j is equal to modulus of I prime is equal to modulus of j prime, and that is equal to 1. So from a dot b is nothing but your mod of a mod of b cosine theta. So this is basically equal to cos theta if a cap a vector mod is equal to b vector mod is equal to 1. So from here this will equal to 1. So x plus this will equal to 0 because I and j are perpendicular to each other is equal to x prime. This will be the angle between I cap and I. So the angle between an I cap and I is theta. So this is cos theta plus y prime. J angle between this is j prime. Okay, and this is x. So this will be the angle between this whole angle between j prime and I. It is 90 plus theta. So this is cosine of 90 plus theta. So your x will be x prime of cos theta plus y prime cos minus if this is minus of sine theta. Okay, so this was one part. So similarly you multiply with j dot and j and take the dot product. So it will give you x dot j x I cap dot j cap. So this is x I cap dot j cap plus y j cap dot j cap is equal to x prime I prime dot j cap plus y prime j prime dot j. Okay, so this is equal to 0, this is equal to y is equal to x prime I cap and j. So I cap is this direction and your j is in this direction. So this is 90 minus theta. So this angle is cosine of 90 minus theta plus j and j is theta. So this is y of cos theta. Then y will be basically your x prime sine theta plus y prime of cos theta. So let's write it these two equations similar. So your x is equal to x prime cos theta plus y, sorry, this is minus of y prime sine theta, and your y will be is equal to x prime sine theta plus y prime of cos theta. So you can write this equation in a compact form in matrix notation is as this: x comma y is equal to cos theta, and this second term will be minus sine theta, this is sine theta, this is cos theta, this is x prime y prime. Okay, so this was the rotation. So this is the transformation matrix, this is the transformation matrix. Okay, so or this is also called the rotation matrix here. So this is the rotation matrix here. Okay, so these were the old coordinates. So these were the old coordinate, and this is the new one. So these are new coordinates. So your old coordinate and new coordinates are related by a rotation matrix. And if you remember, if this was your x-axis, this was your y-axis, we rotated in this way. It was this becomes your x prime and this becomes your y prime. So this was anti-clockwise direction. So remember, this is anti-clockwise rotation. So in anti-clockwise rotation, you get this transformation matrix. So if you want to find the transformation with matrix with respect to x prime and y prime, so let's do it here. So I get x y is equal to your cosine theta minus sine theta, this was your cos theta, this is your sine theta, and this will be x prime y prime. You just invert the matrix, you just take the inverse of this matrix and do multiplication, you will get x prime y prime is nothing but the just the inverse if you get. So it will become cos theta sine theta minus sine theta cos theta, and now this will be your x and y. So this was your rotation matrix, and rotation matrix are orthogonal matrix, and I have defined what orthogonal matrix is in the previous lecture. Orthogonal matrices are, let's say O is an orthogonal matrix, then O transpose is equal to your identity matrix. It means your O transpose is equal to O inverse. You can see these two matrices are just the transpose of each other. Okay, so here we can make a conclusion like this, that all types of rotation matrices will be orthogonal matrices. I'm talking about the real matrices, and their determinant, you know that the determinant of an orthogonal matrix is +1. Okay, so for these types of rotation matrices, the orthogonal matrices have the determinant of +1. So this was the basic of 2 cross. I was dealing with 2 cross 2 matrix. One can write the transformation equation for 3 cross 3 matrix also, which is similar to this. So in 3D, let's write the transformation matrices and three-dimensional rotation. So in three-dimensional rotation, rotation is about a plane. So you have to fix one axis and you then just rotate that plane. So let's discuss some cases. Case 1. So first we are going to discuss when z-axis is fixed. When z-axis is fixed, okay, or the rotation is about z-axis. So let me write in this way, not z-axis fixed. We write rotation about the z-axis, or you can say the xy plane rotates. So for this, the transformation equation that Rx of theta is nothing but cos theta sin theta 0 0 1. This is 0 0 minus of sin theta cos theta. So you see, if you multiply here x prime y prime z prime and you multiply x y z, so z terms remain constant. So that is rotation about z axis. So this was just to write x prime y prime. Let me rub it. Okay, so this was the first case. Let's discuss the second case, case 2, when rotation, let's, is about your x-axis. It means your yz plane moves. So your r uh, z, sorry, rotation about z-axis. Sorry, this will be r of z. So rotation about x-axis will r of theta. So this will give you 1 0 0. I am writing c theta as cos theta, this is cos theta, this is minus sin theta, this is sin theta, 0. Sorry, I did a mistake, it is plus, this is minus. Okay. So in the similarly, if you discuss the case third, that is rotation about y-axis, that is xz plane rotation. So r y of theta, if you calculate it by the same transformation which you get, so you will get like this. So this term will be cos theta, this term will be cos theta, this term will be sin theta, this term will be minus sin theta. Here s theta is sin theta, just for writing my compact notation. So this is equal to cos theta. Okay, so these was the basic of transformation or rotation matrices which we often use in method or in physics or in mathematics, that is to transform the given axis. So see, there are two cases. Let me make it clear. There is a coordinate transformation and there is a vector transformation. So suppose, just a hint of this, let's say this is xy and you have a vector in r. Okay, the first thing is I rotate my coordinate. So if I rotate my coordinate in clockwise direction, clockwise, let's say not clockwise, let it rotate as anti-clockwise direction first. So if I rotate my coordinate as anti-clockwise direction, it's a, if I rotate my clockwise coordinate transform to this, it means that, or it is similar. This is just a picture of how you see the coordinate as transformation. So if you say that the coordinate, that the axis set of coordinates, the xy coordinate is rotated in anti-clockwise direction, it is a similar to if I say that my vector is rotated in this direction, vector is rotated in clockwise direction. So rotation of coordinate in anti-clockwise direction is similar to rotation of vector in clockwise direction, and vice versa for other cases. If you rotate your coordinate system by clockwise direction, or you can say similar statement can be said that the rotation of vector is in anti-clockwise direction. So when you are dealing with the coordinate transformation, you have to, because if you go in anti-clockwise direction, the matrix, so see, if you go in anti-clockwise direction, or in clockwise direction, there is a change of sign in sine theta terms. We have seen that the rotation in 2D plane was in anti-clockwise direction, and we got the term that xy is x prime y prime is equal to cos theta sine theta minus sine theta, and this is cos theta, and this was xy. So if this was an anti-clockwise direction, then we have used this matrix. So if it was a clockwise direction, then we have to use cos theta minus sine theta and sine theta. Sure, do remember this. It was only to emphasize you to notice the angle, the way it is transformed, whether the coordinates are transformed to anti-clockwise direction or the clockwise direction. That's the first thing. And second thing, there is a similarity of two statements, whether I say my coordinates are transforming in anti-clockwise direction, or I can say my this vector is transforming to a clockwise direction. The both are similar, so you have to careful about the using the matrices or the rotational matrices while when you are calculating the transformation or such that things. Okay, so this was the important point to note it down. So you should note it down that this is a similar thing, and you have to be wise while using the direction, or be, or what I say is, uh, be careful with the directions of rotation in anti-clockwise or in clockwise. Okay. So there is, I think, one more concept that we should learn about it. That is a rank of a matrix. How to get the rank of a matrix and what is the definition. So the next topic what we are going to learn is rank of a matrix. Okay, so how to get a rank of a matrix or what? So let's first write as definition. So rank of a matrix is defined as order of the greatest or the largest submatrix having non-zero determinant, Okay, it means that if you have a matrix A, let's call for simplicity, it is a 3 cross 3 matrix. So if the submatrix, let's call, is a first 3 cross 3 submatrix that is only 1 in number. If I call as a 2 cross 2 matrix, then for this matrix you can get 9 such combinations. So this is 9 in number, the total combination. If I cross 1 cross 1 matrix, submatrix, you also get 9 such 9 in number. So you have a 3 cross 3 matrix. So if you have a 3 cross 3 matrix A, then the submatrix, which is a 3 cross 3, is only 1, that all the matrix. So if you want to make a 2 cross 2 submatrix from a 3 cross 3 matrix, so there are 9 such possible combinations. You can work it out through. And if you want a 1 cross 1 submatrix, so there are 9 such numbers, because each number corresponds to a matrix element. Okay, so first you have to find the follow steps to consider the rank. So step 1, that should be follows. First you calculate the determinant of 3 cross 3 matrix submatrix. If this is not equal to 0, then rank of matrix A is equal to 3. And if it is equal to 0, then the rank of matrix A is less than 3, whether it may be 2 or it may be 1. So first you calculate the rank. Okay, now you have step 2. Choose any one of 2 cross 2 submatrix and find its determinant of, and find the determinant of this 2 cross 2 matrix. So let me clear. If the determinant of 2 cross 2 submatrix is not equal to 0, then rank of A is equal to 2. If this is equal to 0, then rank of A must be less than 2. And then you have to check any 1 cross 1 submatrix. If its determinant is not equal to 0, that may be another. That is a special case. If that determinant is equal to 0, there are two causes possible. So if not equal to 0, then rank is equal to 1. Rank of, if equal to 0, that happens only for the null matrix. So this happens only for null matrix whose rank is 0. All the elements of the matrix are 0. Okay, so sorry for this mistake, but I fixed it here. So any one 2 cross 2 submatrix, if the determinant is non-zero, then the rank is 2. So there is one more statement about the non-singularity of a matrix. So if a non-singular matrix, if a non-singular matrix, you remove it, right? For a non-singular matrix, the rank and order of the matrix will be equal. So for a non-singular matrix whose determinant is non-zero, the rank and the order of the matrix will be equal. Okay, so that was the thing. Okay, let's do a quick question here. Let's take a general matrix A. Okay, let me write the matrix very simple for you. 1 2 3 1 2 3, let's say 4 6 6 9. Okay, so if you find the determinant of this 3 cross 3 matrix, you will get 0. Just do it, you will get the 0. Any two subset, if you take like 1 2 2 4, the first subset, its determinant is 0. If you take any this subset, let's say 4 6 6 9, its determinant is 0. So the determinant of 2 cross 2 is also equal to 0. So the rank of the matrix, rank is represented by row, rank of the matrix is 1. So for this matrix, the rank is equal to 1. So that was just the basic transformation equation and the rank of the matrix. So till now, I think we have studied not too much, but something that is just required for the JAM examination, just and TFR examinations in that matrix section. So I suppose that you have learned something from these lectures, not too much, but something definitely you will have learned, and apply these concepts or these types of transformations and these types of relations of matrices in various fields of physics or in mathematics to get more beautiful results. So that was the thing, or that was the uh, topics that one should cover while preparing for these types of examination. So I think this is enough for the matrix section. So in the next video, we will be starting another topic of mathematical physics. And I emphasize you to solve more problems on this matrices, and just do a practice and have a lot of revision. So that will be good for your JAM examination. So don't worry. I think this is all about the syllabus that is taught in the undergraduate courses. So I think I have covered most of them. So you can refer these to your friends who are finding worries in matrices. So this can be used in undergraduation as well as for JAM examination. The both are same. And I tried to give explanations wherever it is necessary for you to, like, why this is happening, what would happen if you do this. So I like this to answer these types of questions, so I put that type of questions and frames. Okay, so it was, hope this will be helpful for you. So stay tuned with us, subscribe the channel, share the channel to your friends. Okay, have a good day. Thank you.